Welcome, ladies and gentlemen. This is your section 7.6 note guide. It's the last note guide of this unit with exponentials and logarithms. This is all about solving exponents or exponential and logarithmic equations. So we've gotten a lot into graphing, being able to solve exponentials as long as we're not solving for the actual variable or the exponent. So you'll see some tricks to solving exponentials when the x or the variable is in the exponential spot. And in the earlier videos, I kind of had already alluded to this. And we had used graphing to actually solve them. And that, while it's fine, it just takes a long time. And this is a much quicker process. This note guide is broken up into two sections. The first part is just showing you strategies on solving. And then the second part is application. And I want to take my time there to make sure I explain how to set up the problems and then solve them. So here's our two objectives: solve a given exponential or logarithmic equation. That's the first thing I'm going to do. And then part B will be write an equation to model an exponential situation and then solve that equation. So before I get into the strategies of solving, and you really do know most everything when it comes to logarithms, there is this one thing called properties of equality, which is really, really powerful with exponentials and logarithmic equations that I wanted to show you. Over here it says exponential equations. You have b to the x equals b to the y, if and only if. Well, if you have b to the x equals b to the y, and they have the same base b, then you can just say, hey, you know what? X is going to equal y. To give you a real example of this is like if you have a to the third equals a same base to the third, obviously 3 equals 3. Or let's say all of a sudden you're saying a to the third equals a to the x. Well, what value for x would make it equal a to the third? Well, it'd be 3. So you would set these exponents equal to each other, assuming the bases, or making sure the bases are the same. So that's really, when it comes to properties of equality for exponentials, that's what we're looking for. So again, here's an example over here. If the base 3 to the 2x equals 3 to the 10th power, you can just set those exponents, because they have the same base, you can set those exponents equal to each other. So I'm setting these exponents equal to each other and solving. So if I solve, I divide up obviously both sides by 2, and you get x is equal to 5. And to test it, you can throw 5 into x, so plug it into x. 2 times 5 is 10, so 3 to the 10th does in fact equal 3 to the 10th. So that is the properties of equality for exponentials. I can do that same thing with logarithms. And I just want to make sure, again, you need to have the same base. Notice here we have the same base. As long as you have a base that's the same on either side of the equation, then you can set, in this case, x equal to y. So you have log base b, x equals log base b, y. Then you can say x equals y. How does that work in a true example? I can show you right here on the right side. If log base 5 of x over 2 is equal to log base 5 of 7, since they both have a log base 5, I can write this as x over 2 equals 7. So you can set those equal to each other, just like we set the exponents in the top equal to each other. And then you can solve it. You can either cross multiply as a proportion or multiply both sides by 2. Bottom line, you have an answer of x equals 14, however you do it. Okay, so that's kind of a quick study on the properties of equality. But you'll see it's gonna pose very, very helpful up down here. So we have two huge strategies for solving exponentials. So notice these are exponentials, these are logarithms. So I'm gonna show you some strategies for solving exponential equations. Now, the first one is, of course, is make the bases equal. So we can use the properties up above, like what we talked about up above, or take the log or natural log of both sides if you can't make the bases equal. So we do first want to make the bases equal if possible. So example 1, it says 4 to the x equals 1/2 raised to the x minus 3. If you look at this, notice the relationship between 4 and 1/2. There's clearly a relationship. They both have that 2 that can be divided into 4, and 1/2 can be represented as 2 with a negative exponent. So I'm going to be using strategy number 1 here. So I'm using strategy number 1. So I'm going to rewrite 4 as 2 squared. Okay, so I'm rewriting the 4 as 2 squared, and then I know that's raised to the x power. So all I'm doing is rewriting this right here as 2 squared instead of 4. Same thing on the right side. Instead of saying 1/2, I'm going to write it as 2 to the negative 1. Again, because we know 1/2 is the same thing as 2 to the negative 1 raised to the x minus 3. Now, if you look at this, what we've done is we've created the same base right here. And so we have made the bases equal. So now I can, and I'm going to highlight this, I'm going to set these equal to each other. Now keep in mind this the whole exponent. So I'm going to go, and you know what, I'm going to even look at this. I can change this to look like my highlighter. So 2x equals negative 1 x minus 3. So all I'm doing is, since we have the same base, we are setting that into creating a linear equation with it, and we're solving for the exponents. So I'm distributing. So I have 2x equals negative 1x plus 3. Now I'm consolidating, or obviously solving algebraically. 3x equals 3, so I'm moving that negative 1 over, and then I have x equals 1. So that, my fine young ladies and gents, is your solution. So if you put 4 to the first, you'll get 4, and if you put 1 in for x, you'll get x, or you'll have 1/2 raised to the negative half, which is the same thing as 4. Okay, so that example is an example of the first strategy. The second strategy right here, well, let's just explain why you can't use the first strategy in this one. If you look at this one right here, I'm going to use strategy number 2, but it's because I can't change 11 to have a base of 4. So 4 to what power would give me 11? Nothing. And I could maybe break this again down to 2 squared x to the raised to the x, but I couldn't change this one to 2 to any power. It just doesn't work. So because of that, I'm going to show you a different strategy. Now, if you notice the top one, you didn't need to use a calculator, and that would be on a no calculator portion. This one, example 2, would be on a calculator portion. So I do want to make sure you see the difference between the two. So this strategy right here is that you take the log or natural log of both sides of the equation. So I'm going to take the log of 4 to the x, and I'm also going to take the log of x. So it's almost like doing, you keep it balanced by doing the same operation. That's exactly what we're doing here. Now we know by our power properties, or excuse me, I keep saying power properties, logarithmic properties, that we can take this exponent and bring it down front. So you have x log 4 equals, oh, you know what? I just realized, and you're probably all going, she put 11 or x instead of 11. Sorry, you guys, let me rewrite that. So this should have been 11 right there. So log 4 to the x equals log to the 11th. I literally just took the log of both sides of the equation. Then I brought the x forward using the the power property of logarithms, the third property, if you want to remember it that way. And then I can solve for x by going log of 11 in my calculator divided by log. Oops, I'm going to erase that so I have a little more space. And I'm erasing everything now. Log 4, and then you throw that in your calculator and you'll get the answer 1.73. Now, the interesting thing now is that you have more tools in your tool belt to do lots of different things with these logarithms. I do want to say that another strategy, which I didn't put up there at the top, but another strategy is if you switch this over to exponential form, you can go, or excuse me, if you switch over to logarithm form, you can say log base 4 11 equals x. And if you do that, now you notice you don't have it in your calculator to go log base 4 11, But what you can do is use your change of base. And I do want to say I'm aware that some of the calculators allow you to change the base in your calculator. On assessments, especially as we're getting into pre-calculus, you have to either show how to do it by the first method I just showed you over here, or by the change of base. And in that case, I want to say log 11 divided by log 4. The reason being is the calculator has programmed the change of base in there, and I worry that you are not understanding that what it's doing is running the change of base formula. So you would have to either show, I'm just kind of making sure that there's no miscommunication, you either have to show this type of work in an assessment, or you have to show this type of work in an assessment. And it doesn't matter which, but you need to show one of them. Okay, so you can't just go right away and just plug it into your calculator. I need to make sure there's understanding there. And of course, you in this case would get 1.73 as well. So in example number 2, you have choices, but in either respect, you are having to change the base somehow, or again, take the log to both sides and use the calculator to solve it, unlike example number 1. And example number 3. Now again, I could just say, hey, you can just do the log to both sides and blah, 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 blah. But if you can change the base, I expect you to do that. So what I'm saying is here, you see the base is 9, the base is 27. Are they related? Of course they're related. They can be both written with a base of 3. And that is going to go a lot further next year when you're in pre-calculus than any other kind of idea. So I need to make sure that you're getting that kind of practice. So 3 squared is 9. And then we, of course, now all I did was rewrote 9 there. So I have 2x up there as well, equals 27 is, of course, 3 cubed. 3 times 3 is 9, times 3 is 27. So 3 cubed and x minus 1 right there. And this, of course, again, would be in a no calculator part. So just a reminder that I am, oh, and I don't like that highlighter nearly as much as my little pink one. So this right here is what we can set equal to each other now because we have the same base of 3. So I am going to be consistent with my colors. I'm going to go 2 times 2, well, I'll write it out. 2x equals 3 times x minus 1. And I end up with 4x equals 3x minus 1, and then we can solve it really quick from there. And you end up with what we have. Gosh, I've been doing all sorts of little things wrong here, aren't I? It's as if I'm testing you, but no, I'm just making mistakes. So 3x minus 3, and then we end up with x equals negative 3. Yay! So there are our 3 solutions for example 1, 2, and 3. Notice that of the 2, I used that strategy 1 for both example 1 and 3, and then strategy 2 for example 2. Okay, so let me keep on going. Let's see how you're doing with this. I'm going to erase this right here though, so you can kind of see what I'm doing. That does say log. I'm going to take more time than sorry. Okay, so now we're going to solve logarithmic equations. So notice we have 3 strategies over here. We have use the property of equality, so kind of the same base, just like what we did above in example 1 and 3, or write it in an exponential form and solve it from there. So once you switch it into exponential form, then you can do just like what we did in example number 2 up above. Or use your logarithmic properties to combine into a single log and then solve from there. So let me just show you each one of these type of strategies. The first one is definitely going to be this right here, this one. And so I'll call it strategy number 1 if you will do it that way. Now, the reason I know instantly it's that strategy is because we have a log base 5 on both sides. Now, of the equation. So as soon as you have a log on both sides of an equation, notice this one's not like that. We don't have a log over here, and here we don't have a log over there. Because of that, where you have a log on both sides, that's how I know that we're going to use that equality, property of equality. So we have the same base, so I'm going to write it 4x minus 7 equals x plus 5, and it's as simple as solving this algebraic equation. Back to the good old days, right? And it's all because of that same base. Now, the one thing I need you to really, really understand about solving logarithms is that you do need, there is no exception to this, you need to show that, oops, I shouldn't cross it off. I thought I was highlighting, sorry. You do need to show the check. And the reason being is that you sometimes get solutions that aren't actually solutions. You get these things called extraneous or extra solutions. So that is one of those things that I need to remind myself sometimes. But logarithms, just like when you're solving radical equations or square root equations, you need to check those equations or check the solutions always. Okay, so I'm going to solve this really quick. I have 3x equals 12, and we end up with x equals 4. And to check it really quick, I know I have log base 5. Let's see if I put 4 in there. 16, we end up with log base 5 of 9 equals, and now I'm going to put 4 into this one right here. So we end up with log base 5 of 9. And do you have to show it? Not necessarily, but you know what? I just want to make sure you understand how to show a check, because that's something that we haven't talked really all that much about. Okay, so that is all good. This does make sense, so that is my solution. So x equals 4. That is the solution for x. Example number 4, again, you can't use that first strategy, but you know what I might do is switch it over to exponential. That's what I tend to like doing all the time. So I'm going to go 4 to the third power equals 5x minus 1. And now if you look at that, notice that the x is no longer in the exponential spot. So at this point, you could just solve that as an algebraic, nice linear equation where 4 cubed is 64, and then solve it from there. So we have 5x minus 1, 65 equals 5x. So we have x equals 13. And again, I really would not cloud this or say it's a solution until you check it. So I'm going to put 13 right in. I'm going to actually say check right here since it's your note guide, and I'm going to actually write check up here as well. So I have log base 4. I'm putting 13 in for x. So 13 times 5 minus 1 gives me that 64. And 4 to the third power does in fact give me 64. So this checks out. So 4 to the third is 64, or log base 4 64 is equal to 3. Good. Now we have this last example here in this section. We have log 5x equals log x minus 1 quantity equals 2. Now again, there's no log on the right side, so I cannot use that first strategy. Notice that we have a plus here, right here. So this is when we're going to use this strategy right there. So again, we use the first strategy there, we use the second strategy there, and we're using the third strategy here to start with at least. So I'm using my logarithmic properties. I obviously say power properties a lot more. So I'm going to combine them. So I have log 5x times x minus 1. So because of the addition, we know it's multiplication when you combine them or condense them. That equals 2. Now I'm going to simplify this. I'm going to actually distribute my 5x through the parentheses. So I have 5x squared minus 5x equals 2. Now this is going to be where you're going to look at this and go, ugh, what am I doing now? Well, this is where you're going, now actually let me stop here. There's no division in here. You're not going to all of a sudden say log 5x squared divided by 5x. You can't do that because you don't have a log 5x squared minus a log 5x. I see that all the time, and you don't want to do that. This is a quantity, 5x squared minus 5x. And at this point, what I always tell students is if you're looking at it in its log form and you're like, I don't know, I would highly recommend switch it over to exponential form. So really we're using strategy number 3 and strategy number 2 here, if we numbered these, if this was strategy 1, 2, and 3. So I have 10 squared equals 5x squared minus 5x. And then we now have an actual equation that's not an exponential. An exponential equation is where you have an exponent in the like a variable in an exponent spot. So example number 4, that's kind of what I was saying, is we went from a logarithmic, when we switched over to an exponential form, we actually ended up with a linear equation. Well, in example number 5, when we used the properties and then switched over to exponential form, we actually don't have an exponential equation. We have a quadratic equation, because the highest power here in the exponent with the variables is 2. So I know 10 squared is 100. I'm going to set it equal to 0 because that's what you do with all quadratics. So I have 0 equals 5x squared minus 5x minus 100. So this is where that first semester advanced algebra and that algebra 1 really is going to show, because this is where you need to know your quadratics. So notice we're bringing in the linear equations, we're bringing in the quadratics, sometimes there's even other kinds of equations. So it all kind of ties in together, and it's kind of what makes the class sometimes a challenge if you're not remembering your material. Okay, so this here, you can try factoring this right away. You can use the quadratic formula. What I'm going to just say though right away is that I notice that there's a 5 here, a 5 here, and 100 that's divisible by 5 there. So I am going to divide everything, both sides of the equation to keep it equal, by 5. And if you did it in the first step or right above there, that's fine as well. But I'm just letting you know this is really makes it much easier. So I'm going to actually bring it this way. I know this is kind of bothersome, but so I end up with 0 equals x squared minus x minus 20. And that makes a much easier equation to factor. So I'm just now looking at it, I'm like, hey, I'm going to factor this really quick. Just a couple things about factoring. Make sure your variable squared is a positive. That makes factoring much easier. And again, get rid of common factors like I just did if possible. So I'm not going to tell you how to factor because you were taught all sorts of different ways on how to factor. But I know this is an x, this is an x. And then we have minus 5 and plus 4. So if you use the cross method, the box method, all sorts of different methods, trial and error, you know, it's all good. But you should be able to factor this pretty quickly. At this point, of course, to solve, you're setting each factor equal to 0. So x minus 5 equals 0, x plus 4 equals 0. So this one's going to be x equals 5, and this solution is x equals negative 4. Now, this is where, like I said, you need to check. Because if you put 5 in, you end up with log of 55 plus log of 54. Combine them, and it will check out. That'll be great. But I'm just letting you know, if you put negative 4 in for x, you end up with log of negative 20. There is no such thing as log of a negative number. So, and if you think about this, 10, because this is common log, right? 10 to what power will ever give you a negative 20? Well, when you go log 10 to a negative exponent, you get a very small fraction, and it gets closer and closer to 0, but it never actually, you never even get to 0 because of that asymptote idea that we showed with graphing. So I'm just letting you know that there is no such thing as a negative log. So you can't take a log of a negative number, I should say. And again, the reason is graphically, you can't even get a negative because you have, it gets closer and closer to 0. But you need to check it, otherwise you're just going to say, hey, that's a solution, and that's going to be where you're going to go wrong. So let me just kind of go back here. So we have x equals 5 as the solution right there. Okay, so this is a biggie because you're using your logarithmic properties condense. Then from there, you're switching over to exponential form. From there, you need to remember your quadratics, especially the factoring. And then from there, make sure you look at what you have and check in your mind or physically to see if it's actually working. So this one, even though it looks like we have two solutions, you only get one that makes sense, which is x equals 5. Okay, so that's it for this part. So I wanted to show you the strategies of solving logarithmic equations and exponentials. And the second video is going to be all about application, which is fun. So we'll talk to you then.